So good evening to one and all. Is the audio clear? And video also? Thank you. So any queries over the previous class? Anyone on the concept of subgroups and others? So have you read the material which is given to you in Telegram with regard to the theorems on subgroups? The necessary and sufficient conditions, where you have taken that H inverse is a subset of H inverse equal to H, etc. Have you seen them? Is it comfortable to understand? To follow the solution? Fine. So let us begin our today's session. Let us take H1 and H2 are two subgroups of a group G. So my intention here is the intersection a subgroup or not? That was the question. So here the answer is yes. Because if you take two subgroups of G, as we know, the identity element in the group and subgroup is always same. The unique value you will get. If you take E is the identity element, then E will belong to H1 and E will belong to H2, the identity element. Hence, it will belong to the intersection. So, intersection is a non-empty set. If you want to prove that it is a subgroup, apart from verifying closure, associative, identity and inverse, we can make use of the necessary and sufficient conditions. So the condition which is most popular is AB inverse belongs to H, because you may take the finite set or infinite set, the intersection, whatever the case may be, this is the common checking test whether it is a subgroup or not. So if you take two elements A and B in the intersection, I have to prove that AB inverse will belong to the intersection, so that intersection will become a subgroup. Since you are taking the elements in the intersection, so you have AB belongs to H1 and AB belongs to H2. Since H1 and H2 are subgroups, so you have AB inverse belongs to H1 and AB inverse belongs to H2. So it will belong to the intersection. Therefore, H1 intersection H2 is a subgroup for the group G. Right? You please take a note of it. After noting, please tell. So any queries over this approach to anyone? Say. Any doubts, any queries? Please take a note of it. So, using the similar logic, you can say that if you take a set of subgroups, H1, H2, so on, Hn, then all their intersection, H1 intersection, H2 intersection, so on intersection Hn, is also a subgroup. Using the same logic, we can prove that. If you take a set of subgroups, their whole intersection is nothing but again a subgroup. Using the same logic, we can prove. In a simple way, we can say that if you take a family of subgroups, the intersection of the family is again a subgroup. Now the question arises that if you talk about the union, is the union an intersection, a subgroup or not? Is the union a subgroup or not? That was the question which is before us. For example, you take z comma plus the integers group. Let us consider two subgroups, H1 and H2. You take all the multiples of 2. You take all the multiples of 3. So these are subsets of Z and these are subgroups. Can you confirm, are they subgroups or not? The multiples of 2 as well as multiples of 3. Right? You can check out the condition AB inverse. So, if you consider the union H1 union H2, so you are writing all the 2 multiples as well as 3 multiples here in single set. Is it a subgroup or not? That was the question. I will say that it is a not subgroup, because if you take the 2 multiple, if you take the 3 multiple, the operation is plus. If you add them, the result is 5, which does not belong to this set, because 5 is not a multiple of 2 and not a multiple of 3. Agree? So here closure law fails by default. So at this point, our interesting thing is, as and when you consider a union, sometimes it will become a subgroup, sometimes it need not be a subgroup. So if you want to say that firmly, whether I have taken 2 subgroups, the union is again a subgroup, then what could be the condition satisfied by the sets H1 and H2? So I repeat, I have taken 2 subgroups, H1 and H2. If the union should become a subgroup again, then what is the property should be satisfied by H1 and H2? Is that clear? Say that we are going to verify now. It is also a small result. Let us discuss on this. So here the question is H1 union H2 is a subgroup if and only if either H1 subset of H2 or H2 subset of H1. So this is one of the good results, you can say. If you want to say that the union is a subgroup, you should say that one must be a subset of the other in the two sets. Then only union will become a subgroup. That's it. Otherwise, union need not be a subgroup always. Okay? Is the question part clear? Please take a note of it. Now we are going to prove this part. After noting, please let me know. So if you observe that it contains two parts, main part as well as converse part. Let us start with the converse part first. So we assume that either H1 subset of H2 or H2 subset of H1. Now here what happens, suppose you consider the first case H1 subset of H2. Then what will be the union of H1 union H2? Can I say that the union is nothing but H2? Because among the two things, this is the bigger one. So if you consider the union, it is nothing but H2. Similarly, if you take the second case, H2 subset of H1, then in that case, union is nothing but H1. So whatever the case you consider, the union is equal to one of the sets, H1 or H2. Initially, you have considered that H1 and H2 are subgroups. Since these two are equal, union is also a subgroup. Is it clear? Why the union is a subgroup? Because it is equal to one of the sets. Now, if you take the main part the other way, you suppose that union is a subgroup. So I need to show one of the sets is a subset of the other. I don't know what is actually H1 and H2, what is the operation I am dealing with, etc., etc. So I am proving universally that if union is a subgroup, one must be the subset of the other. That I have to prove. Since there is no direct proof available with me, I prove this by the method of contradiction. So what it is? I assume that this part does not hold. So we are assuming that that condition does not hold. So while doing the process, you will get a false answer. We call it as a contradiction. Therefore, our supposition must be wrong. Hence, either H1 subset of H2 or H2 subset of H1 must be true. Okay? That is the strategy I am applying here to prove that. So, as per our supposition here, as we have taken that H1 not a subset of H2 and H2 not a subset of H1, what we can say about the sets? What are the elements you consider? What we can say about the sets? Are they totally distinct? Do they have common elements? So what we can say about them? Can you specify? Any one of you? There is no need to be disjoint. May or may not have common elements. That's true. Then let us have a small example that you take H1 is equal to 1, 2, 3. You take H2 is equal to 1, 2, 4. So at this perspective, can we say that H1 subset of H2? No. H2 subset of H1? No. Agree? So whether they may have common elements or not, that doesn't matter. We can say one thing, that there should be at least one element in H1 which is not there in H2. So which is belonging to H1 exclusively. Similarly, there is an element H2 which does not belong to H1. Agree? So that we represent mathematically. So we can say that there exists A belongs to H1 such that A does not belongs to H2, and there exists B belongs to H2 such that B does not belongs to H1. But the elements belong to the union. So as per our supposition, union is a subgroup. This is our consideration, our assumption. So by closure law, the product AB belongs to the union. So any doubts up to this part? To anyone? Please take a note of that. All right. So if you want to draw a small picture for your understanding, this is H1, this is H2. I took an element A in H1 which belongs to H1 only, and this is the element in H2. But we have, by closure law, the product AB belongs to the union. So that product may belong to any set. So if you multiply both A and B, you will get a result. The result is belong to the union. So AB may belong to this place or to both. Agree? Yes or no? So these are the possible cases for you. AB belongs to H1, AB belongs to H2. Because as in when you say that an element is in the union, it must belong to one of the sets at least. That is common. You should not avoid that. So if you take AB in H1, since A belongs to H1, you can say that A inverse also belongs to H1. Because H1 is a subgroup. You got two elements in H1. One is A inverse, one is AB. So A inverse AB belongs to H1 implies A inverse A into B belongs to H1. Do you agree for this? So, is this true? No, because B is in H2 only, not in H1. Agree. This is our starting line. Yes or no? So, this is a contradiction. Now what happens? This case is not correct. Now take this case. So we have the diagram like this. Suppose you take that AB belongs to H2. Since B belongs to H2, we can say that B inverse belongs to H2. Therefore, AB into B inverse belongs to H2. Since closure law. Since H2 is a subgroup, the inverse of every element will belong to the set. So again you have applying associative law, A into B, B inverse belongs to H2. Again this is a contradiction because A does not belongs to H2. So whatever the case you are considering, you are always getting a contradiction, isn't it? Therefore, our initial supposition must be wrong. Therefore, it must be either H1 subset of H2 or H2 subset of H1 is mandatory. Because earlier you have started that this is not correct. So while doing the process, you get a contradiction. Whatever the case you consider, you are getting a contradiction. Therefore, our initial supposition must be wrong. Hence, either H1 subset of H2 or H2 subset of H1 is obvious. That is the conclusion. Okay? So you please take a note of it. Then I discuss with the other concepts. After noting, please tell. So is everyone clear with this approach, or you want any more explanation? Fine. Now let us take some sample problems on our discussion so far considered. So let us take the case that Z6 you take, operation is addition modulo 6. Now prove that S comma T are subgroups of Z6. So for this problem, what is the approach for the solution? As per the previous class and present class discussion, you please tell. what is the approach to show that S and T are subgroups of Z6? Anybody? How can we prove this? I have given the set, I have given the operation. The question is, we have to show whether they are subgroups or not. AB inverse belong to subset, right? That is one good practice. Can you say any other practice than this? A simplified practice rather than AB inverse. So here I say that whenever you have a group and a subset, if you want to check whether it is a subgroup or not, we are going to make use of two conditions. One condition is AB inverse belongs to H. The other condition is AB belongs to H. Agree? So, the first condition we use generally for the infinite case and for finite case also. For the second condition, we use this for the finite case. If the closure law is satisfied, then immediately we can say that it is a subgroup. So here, if you observe that this is a finite group and these are nothing but the finite subsets. So as one of our friends mentioned, if you construct the composition table and verify the closure law is satisfied or not, immediately you can say that it is a subgroup. Okay? Are you getting the concept? Right. So let us consider the composition table. Operation is plus 6. If you take the set S, the elements are 0, 2, 4. Let us add them. 2 plus 0, 2 plus 2, 2 plus 4, 4 plus 0, 4 plus 2, 4 plus 4. So as per the operation considered, this is the composition table. Agree? This is the operation addition modulo 6. So if you observe that the entries in the composition table, are nothing but the values of S. You didn't get any value beyond S. Therefore, closure law is satisfied by S. Hence, by the necessary and sufficient condition, we say that S is a subgroup of Z6. Similarly, for T also, we will construct the composition table. We get the same value that the entries in the composition table are nothing but the elements in T only. Therefore, T is also a subgroup. Okay? Clear? So after constructing the composition table, we mentioned that since all the entries in the composition table are elements of S only, therefore closure law is satisfied by S. Hence, by known result, S is a subgroup of Z6. So in the exam, you need to mention the result also. As per this result, I am stating that S is a subgroup of Z6. Okay. You please take a note of this. And my question here is S union T is a subgroup or not? you please check and tell me, is S union T a subgroup or not? Not. Why? Because as per our discussion earlier, S is not a subset of T and T is not a subset of S. The subgroup for the union is possible only when one set must be subset of the other. That case fails here. Just now we have proved a result, isn't it? So as per the result considered, since S is not a subset of T and T is not a subset of S, immediately we can say that S union T is not a subgroup. That's all. There is no need to write the composition table here. Please understand. So here, while proving that S union T is not a subgroup, we have two techniques. One technique, S union T is nothing but 0, 2, 3, 4. For this set, you draw the composition table. So in the construction, you will get an element which is not in the union. So it is not a subgroup. Clausula is failed. Second thing, you state the result what we just proved. Union of two subgroups is a subgroup if and only if one set is subset of the other. So by stating the result, immediately we can say that S union T is a not a subgroup. There is third approach also. Apart from constructing the composition table, we can say that 2 and 3, both numbers belong to S union T. If you consider the closure law, 2 plus 6, 3 equal to 5, which does not belong to the union. So by simply saying this condition, we say that closure law is failed in the union, hence it is not a subgroup. So you can prove any manner by taking a counter example, by drawing the composition table, by stating the previous result. Anything you can do. There is a good part of abstract algebra. So if you know the fundamentals correctly, you can state any one fundamental. Based on that, you are concluding or validating a statement. That's all. Okay? Is it clear for you? Right. Now let us discuss the other case also. Suppose you take that G is equal to set of all non-zero real numbers. Operation is multiplication. And you take the set of all elements in G which are greater than or equal to 1. Now the question is H a subgroup or not? Can you tell? So G contains all the non-zero real numbers. I have taken all positive real numbers, all negative real numbers. Operation is multiplication. If I take H like this, is H a subgroup of G or not? So one of our friends replied that it is not a subgroup. Can you specify the reason? Can you specify the reason for it? On what basis you are saying that it is not a subgroup? Alright, AB inverse does not belongs to H. That is also true. Your approach is correct. You can say one more thing. If you want to say that H is a subgroup, you need to verify closure, associative, identity, inverse. Since you are taking all the real numbers greater than or equal to 1, you take any real number, say 5. So what is the inverse of 5? Nothing but 1 by 5. Right? Now the question is 1 by 5 belongs to H or not? That's it. Because you are taking all the real numbers starting from 1 onwards. Please understand. So 1 by 5 is a real number which is smaller than 1. Therefore, 1 by 5 does not belong to H. But 5 into 1 by 5 is equal to 1. So this is the inverse of this element. Clear? So you can verify the condition AB inverse does not belong to H. That is also correct. Apart from this, you simply take an element and you can prove that. That is also correct. H inverse is not equal to H. Therefore, it is not a subgroup. That is also correct. So you have multiple ways to prove or validate a statement. Please understand. The examples why I am taking here means, apart from the traditional thinking, you can do anything based on a standard result or verifying the definition, anything you can do. So you can validate a statement whether it is correct or not. Okay? That's it. So I want to take one more example so that I will conclude the problems part. I will take one more result which is also important, asked in the previous papers. So earlier we have solved a problem that if you take set of all ordered pairs AB where the first coordinate A not equal to 0, then the operation between the ordered pairs is defined in such a manner that this is the operation on the ordered pairs. Can you recollect that? We have proved that G is a group with the operation defined like this. Can you remember that problem? Right. So here, since A is not equal to 0 means, if you consider the two-dimensional space, excluding y-axis, I am taking all the 4 coordinates. This is nothing but our given group. So I am excluding y. So let us take a set in the 2D space. So I am taking all the ordered pairs H as set of all ordered pairs 1 comma B such that B belongs to R. So here I have fixed the x coordinate and B may be any real number. So is it a subgroup or not? Can you verify that? Yes or no? So here the approach is nothing but, as you mentioned earlier, A dot B inverse belongs to H. Because you cannot straight away pick up one element and you can check because this is an infinite set. So we are going with the checking condition A dot B inverse belongs to H. So what it means, you take two elements, first element into second element inverse must belong to H. So let us take, if you take the ordered pairs, say 1 comma B, another ordered pair 1 comma C belongs to H. So what we need to check, we have to verify X dot Y inverse belongs to H or not. What I am going to verify? Yes or no? So this is the checking condition. First element into second element inverse. If this value belongs to H, immediately we can say that H is a subgroup. Otherwise not. So if you observe that, what is the inverse of Y in that set? Can you say? What is the inverse of Y in that set? You have verified inverse property in that problem that whenever you take an ordered pair AB, the inverse is nothing but yes or no? Did you recollect that formula? Did you recollect that formula? Say. So here, for, are you getting the idea or not? So here for 1 comma C, the inverse is nothing but 1 by 1 comma minus C by 1. Agree? So here the inverse of Y is nothing but 1 comma minus C. So if you apply the product X dot Y inverse, it is nothing but so you have to do the multiplication defined like this. It is nothing but 1 and B minus C. And how H is defined? H is defined in such a way that the first coordinate is 1, second coordinate will be any real number. So here is also the same format you got. The first coordinate is 1 and second coordinate is any real number here. Therefore, this value belongs to H. Hence, it is a subgroup. Is it clear? How we have verified the subgroup part? So you please take a note of this. Then we are going to prove a small theorem. So then we conclude this part. Then we move to an interesting thing. After noting, please tell. So here, let H comma K be two subgroups of a group G. Then HK is a subgroup of G if and only if Hk is equal to Kh. So this is also one of the previous year problems. You please take a note of it. So we discuss about the procedure. So initially H comma K are two subgroups of a group G. So immediately you recollect the results what we have learned in the previous classes, and we are going to consolidate these things for H and K. So we can say that H inverse is equal to H. I can say that H is equal to H. H inverse equal to H. So all these results are applicable for H. Agree? Because H is a subgroup. We have learned some of the previous results. Similarly for K also, K inverse is equal to K, K inverse equal to K into K equal to K. So these are the set of results which are known to us. So this result contains two parts, main part as well as the converse part. We have to discuss the both. So let us consider the converse part first. So let us suppose that Hk is equal to Kh. So our claim is Hk is a subgroup of G. How can we prove this? Can you tell? As per these results considered, any ideology in your mind to prove to anyone? So here I will say that among the results what you have written, this is a normal condition. This is if and only if condition. Say, have you seen the material posted to you? So H is subgroup of G if and only if H is equal to H. H is subgroup of G if and only if H inverse is equal to H. Yes or no? So the ideology from that results is nothing but, so if you have a set A, if you want to prove that A is a subgroup, you should prove A into A inverse is equal to A again. If you take this result. Similarly, if you have a set X, you want to prove that X is a subgroup, then you have to show X inverse is equal to X. Are you getting the ideology? So here also, if you want to prove that HK is a subgroup, you have to prove HK into HK inverse is equal to HK. You have to prove that. If you are able to show that equation, then as per the necessary and sufficient condition, we can say that HK is a subgroup of G. So here, please understand that HK is the product of two sets where each element in that set can be written as product of two elements where first element belongs to first set, second element belongs to second set. That is the actual meaning here. So by default, you are using dot means whatever the operation is there on G, the same operation is between the sets. Please understand that. Okay? What you said is correct. If operator is plus H plus H plus K you take. That's all. So your intention is correct. What you thought is correct. Fine. So is this idea clear for everyone? Okay. So you consider HK into HK whole inverse. So this can be written as HK. This is nothing but as per the properties of complexes I have stated earlier. K inverse, H inverse. As we know, K inverse is nothing but K. This is equal to H, K, H inverse. Our supposition is HK is equal to KH. So this is equal to KH, H inverse. Again, this is nothing but KH because H inverse is equal to H. So these two things I have used here. This is one, this is one. Again, this is equal to HK. So you can write like this, the since part. This is so here. Then you have, again you have is it clear now how it is written? Therefore, HK into HK whole inverse is equal to HK, which you got. You please take a note of that. Hence, by necessary and sufficient condition, HK is a subgroup of G. So if you are clear with this converse part, then I discuss the main part. After noting, please tell. Any doubts or any queries for anybody on this part? All right. So if you consider main part, you assume that Hk is a subgroup of G. So immediately among these results, you can apply one result. So I am going to apply the first result. So I say that Hk whole inverse is equal to Hk. So immediately you can say K inverse H inverse is equal to Hk. Implies Kh is equal to Hk. That's all. That is the proof. So main part is very simple. Converse part, you need to apply the logic. That's all. So for this problem, the weightage is nothing but 15 marks in UPSC. If you prove main part and converse part subsequently in a correct manner, you will get 15 marks. That is the weightage of the question. Now you can understand the priority of abstract algebra in the scoring. Whenever a result is given, immediately while writing very less number of lines as a solution, you will get more number of marks. The total solution is just like 4 to 5 lines as per the space allocation, if you consider, but you will get 15 marks. That is the best advantage of abstract algebra compared to other parts in syllabus. Do you agree or not? Apart from calculating a lengthy problem by means of a formula, it is very easy. Chance of error is very low because you are not doing any formula substitution, calculation, any XYZ you are not at all doing. You are simply presenting the logic step by step by means of a previous result. If the result is in your remembrance, you are able to recollect the result, then immediately you can write it in a correct manner, you will get good score. No doubt at all. They're the best part of abstract algebra. You will never make a mistake. The worst part is you can totally forget the logic. So if you compare the comparison between abstract algebra and other things, so if you do a problem, if you have done half of it, if the evaluator is good, you will get half of the marks. He cannot strike it off entirely, right? But here, the worst part is you cannot write a single sentence out of the statement which is given there. The best part is with short number of lines, you can write the total answer, you will get the good score. Exactly. No calculation mistake will come here. So at this part, I want to start a new topic, that is cosets. Which will be very interesting for us. What are the importance of cosets with regard to abstract algebra? We will discuss. Suppose you take a group G and you take a subgroup H. Now, you take one element in G, multiply each and every element of H. So this is called left coset. And if you write like this, it is called right coset. See, the element is on the left side, so you are saying left coset. The element is on the right side, so you are calling right coset. Immediately you can ask, is AX is equal to XA or not? If you talk of numbers, if you take the regular multiplication as the operation, it is correct. If you take the element as matrices, is AX equal to XA? So for numbers, it is correct. For matrices, it is not correct. For polynomials, maybe it is correct. For functions, f circle g is equal to g circle h, can you say? So be careful that always left coset, right coset need not be equal. They are different in one way. So here the operation is multiplication. If you take the operation is plus, then how do we define the cosets? Left coset is a plus h, defined by set of all a plus x such that x belongs to h. Right coset is defined by h plus a. So for the operation, if you write the element on the left hand side, it is called left coset. If you write the element on the right hand side, you call it as right coset. Okay? So if the operation is star, you define the cosets accordingly. Is it clear for you how we are defining them? So if we are clear with this definition, let us do one small problem so that we will have good understanding over the concept of cosets. So for operation plus, depending upon the operation and elements, it is equal. Otherwise, you cannot say. Please understand. For numbers, it is true. For matrices, it is true. Please understand, if you talk of normal addition, normal multiplication, normal operations, if the operation is defined somewhat different, you cannot say. Because earlier, I have taken the ordered pairs AB and CD. I have multiplied them in a different manner. So if the operation is somewhat different like this, can you say that for always operation plus, they are equal, left and right cosets? You cannot give guarantee.